Now that we talked about one-to-one and onto linear transformation, we're going to introduce the concept of isomorphism. A linear transformation like T that maps V to W, that is a one-to-one and onto at the same time, is called isomorphism. Moreover, if V and W are vector spaces such that there exists an isomorphism from V to W, then V and W are called isomorphic to each other. We have a nice theorem. Isomorphic spaces and dimension. Two finite dimensional vector spaces like V and W are isomorphic if and only if they are of the same dimension. So again, if you have two vector spaces like V and W, and they have finite dimension, they are isomorphic if and only if they have the same dimension. Okay, that's an interesting theorem. Using this theorem, we can claim that the following spaces are isomorphic to each other. The 4 space and the space of all 4x1 matrices. The dimension of this space is 4x1, which is 4. The space of all 2x2 matrices, 2 times 2 is 4. P3, which is the space of all polynomials of degree 3 or less. Remember that this guy has the bases 1, x squared, and x cubed. That's why it is of dimension 4, not 3. It's a usual common mistake for students that they think, okay, 1 doesn't exist. So it is 4-dimensional. And also the vector space of all 5 tuples, x1, x2, x3, x4, comma 0, such that xi is a real number, which is basically a subspace of the 5 space. But again, here you only have 1, 2, 3, 4 components. The last component is equal to 0. So based off of this theorem, since these vector spaces are all of the same dimension, they must be isomorphic. It means that there is linear transformation. You can define linear transformation from this space to this space that is one-to-one and onto. You can define a linear transformation from the very first space to the third space, which is one-to-one and onto. You can define a linear transformation from the first space to the fourth space, which is one-to-one and onto. And you can just follow the same process. Define a linear transformation from the vector space of all 2x2 matrices to V, that is one-to-one and onto, and so on. That basically connect these spaces together using isomorphism. Standard matrix for a linear transformation. Suppose you have a linear transformation T that maps Rn to Rm, or n space to m space. Be a linear transformation such that for the standard bases, which denoted by vectors E sub I of n space, T of E1 is the column A1 and 1, A2 and 1, AM and 1. T of E2 is A1 and 2, A2 and 2, and so on. And you can define T of En. Then the M by N matrix whose n columns corresponds to T of E sub I, such that TV is equal to AB for every vector V in Rn or n space, is called the standard matrix of linear transformation T. So again, guys, note that this linear transformation maps n space to m space, and here you have m by n matrix. Now, suppose you have the following linear transformation. It maps the space to the plane. This guy says, hey, I'm going to take a vector x, y, and z and gives you x minus 2y and 2x plus y back. This is indeed a linear transformation. You can check to see if it preserves addition and scalar multiplication. Let us begin by finding the images of E1, E2, E3 under this linear transformation. For the vector notation, T of E1 is T of 1, 0, 0. This is how we defined the standard vector 1, 0, and 0. Now plug in everything into the linear transformation. 1 is equal to x, y is 0, and z is 0. So you get 1 minus 0, comma 2 plus 0. So you end up with 1 and 2. So you're going to say that, hey, this linear transformation takes E1 and gives me this column back, 1 and 2. This linear transformation takes E2. It changes 0, 1, and 0 to negative 2 and 1. Again, wherever you see x, you're going to plug in 0. Wherever you see y, you're going to plug in 1. And wherever you see c, you're going to plug in 0 up here. So you end up with negative 2 and 1. Or matrix notation, T of E2 is T of 0, 1, and 0, which is negative 2 and 1. And finally, T of E3, which is T of 0, 0, and 1. Again, the same process. You have your x, you have your y, and you have your z, which is equal to 0 and 0, because z is equal to 1, x and y are equal to 0, 0 minus 0, comma 0 plus 0, which is 0 and 0. It gives you 0, 0 back. So what should I do with this? Well, this gives me the matrix representation for this linear transformation. We expect to have 2 rows and 3 columns because it maps R3 to R2, or the space to the plane. So we expect to have a 2 by 3 matrix that we can see just right here. What about composition of 2 functions, or basically composition of 2 linear transformation? The composition T of T1, which maps n space to m space, with T2, which maps m space to p space, is denoted as T2 of TFV. So it means that you take T1 and substitute that in T2. So T1 is substituted in T2. V is a vector in n space. This composition also denoted by T2 O T1, or basically doing the substitution like this. So again, if T1 maps V to W and T2 maps W to U, you can compose T1 and T2. The composition is going to be a new linear transformation that maps V to W, or in this case, maps the very first vector space Rn to Rp. We have a nice theorem here. if T1 maps Rn to Rm and T2 maps Rm to Rp, and they are all linear transformations with standard matrices A1 and A2, the composition T from Rn, please note that the composition from Rn to Rp defined by T2, T1 is also a linear transformation. Moreover, the standard matrix A for this composition is the matrix product of A2 by A1. So as you compose T2 and T1, you can multiply their matrices and get the matrix for their composition. Definition of inverse linear transformation. If T1 maps n space to n space, and T2 is another linear transformation that maps n space to another n space, such that for every vector in n space, T2, T1, so you're composing T2 and T1. You can also compose T1 and T2. Both of them are identity transformations. If the composition of T1 and T2 and T2 and T1 are both identity transformations or identity function, then you can say that, hey, these two are invertible and they are inverse of each other. So this is nothing but algebra that you learned in intermediate algebra. If you have two functions, if you compose two functions, the output is identity function, then those two functions are inverse of each other. And then we have invertible as well. When we are using invertible, it means that we can talk about the inverse of their matrices as well. Existence of an inverse transformation. Let T from Rn to Rn be a linear transformation with standard matrix A. Then the conditions below are equivalent to each other. First of all, T as a linear transformation is invertible. It means that you can find the inverse for that linear transformation. If T is invertible, then for sure T is an isomorphism. It means that it is 1-to-1 and onto. And 3, if T is invertible, you can for sure say that T is an isomorphism. For sure, you can say that A, the matrix representation for T, is invertible as well. If T is invertible with standard matrix A, then the standard matrix for the inverse of T is inverse of matrix A. For example, take a look at this linear transformation. This linear transformation takes space and map it to the space itself. T of x1, x2, x3 is 2x1 plus 3x2 plus x3. And then the second component is 3x1 plus 3x2 plus x3. And the last component is 2x1 plus 4x2 plus x3. Show that T is invertible. Find the inverse of this linear transformation. So let us begin, everybody. The standard matrix for T is denoted as 2, 3, 2, 3, 3, 4, 1, 1, 1, or 2, 3, 1, 3, 3, 1 if you want to read the rows is 2, 3, 1, 3, 3, 1, 2, 4, and 1. Take a look at your standard vectors, E1, which is 1, 0, 0, E2, 0, 1, 0, and E3 is 0, 0, 1. T of E1 is equal to, so wherever you see x1, you're going to plug in 1. Wherever you see x2, you're going to plug in 0. And wherever you see x3, you're going to plug in 0 as well. 2 times 1 plus 3 times 0 plus 1 times 0, just referring to the very first component, and 3 times 1 plus 3 times 0 plus 1 times 0, referring to the second component. And here you have 2 times 1 plus 4 times 0 plus 1 times 0, referring to the last component is 2, 3, and 2. Next, T of E2 is equal to 2 times 0. Just E2 is 0, 1, 0. Just do the same thing. Plug in x1, 0, x2, 1, and x3, 0. So T of E2 becomes 3, 3, and 4. And finally, if you use the last standard vector 0, 0, 1 and plug that into the linear transformation, it gives you 1, 1, 1. That's how you end up with these 3 columns, which is the standard matrix for this linear transformation. Now, if you find the inverse of this matrix, the inverse of this matrix is negative 1, 1, 0, negative 1, 0, 1, and 6, negative 2, and negative 3. So for sure, since this matrix is invertible, and you could easily find the inverse of the matrix, you can say that T is invertible. Then the standard matrix for the inverse of T is A inverse. But the whole point is how to find a standard matrix for this linear transformation. We need to go back and use the standard basis and convert these vectors using the linear transformation to the columns so you can form this matrix.